Everyone, thank you very much for attending our seminar series from DSRC Security Unit. And today we are really, I would say, fortunate, and I'm personally very happy to have Sebastien Bardin, who is a senior professor researcher at CEA Saclay Paris, where he's a part of software safety and security lab. And I would say that, and also, yeah, so there are many things which are very interesting. I find very interesting about him. He's definitely very, I would say, well positioned as far as security and the traditional formal methods are concerned. So I would say that is something which is very interesting. Like he's coming from a very formal methods background, program analysis, and then a kind of like application of those analysis to security, which is very interesting. And he's also founder of BINSEC group. And actually this is what connects me to him, because when it was getting started at the time, I was part of Verimag team, which is also initially involved in this BINSEC. So while I was about to leave, BINSEC was getting ready for its show. And he is currently like publishing in various diverse communities. So you see that he has publication in top formal methods like CAV, and then you have FSC, and then you have ICSI, and then you have NDSS, which is super interesting. Actually, you don't see such diversified
Whoa. I cannot hear you anymore, Sanjay, sorry. So I don't know if it's from my side or from your side. What happened now? I still have connection or not?
Yeah, I think it's from the Sanjay's side. I'm just gonna
okay. Thank you.
No worries.
I am still sharing my screen, by the way, or not?
Yes, your screen is still there.
Okay. So maybe I wait 1 minute if we can see Sanjay's back, and otherwise I can start.
Yes, exactly. Thank you.
Okay. So hi everyone. So that was very nice of Sanjay for the invitation and the very nice presentation. I will wait 1 minute in case Sanjay can come back. That would be nice. And otherwise, since we have a precise timing, I will start, and hopefully Sanjay will arrive back. So this is a very this is the first time I give this talk, actually. I had the idea of the talk for a while, but this is the first time I do it. So it may not be completely finished. So please be nice with me. I hope it will interest you. Yeah, maybe I will start anyway, Sanjay. No, probably the beginning. So as Sanjay said, I am coming from CEA, France. So CEA is one of the big research institutes in France and one of the 2-3 largest in Europe. So it's about, let's say, art science, physics, biology, so different kind of physics, electronics, mathematics, and computer science. So more especially, I am in the software safety and security lab. So initially, we were developing methods and tools to help people develop safe and reliable software. So typically safety-oriented, critical system. So especially one of the big success in my lab is the Pharmacy open source toolkit, which is used, for example, in production at Airbus. And from myself, from quite a long time now, I am very interested in taking this safety-oriented source-level program analysis technique and try to see how we can adapt them to binary-level security needs, actually, on different the different kind of problems which interest system security people. So what's this talk about? So in a nutshell, I am a big fan of symbolic execution because in some way, when it came back in light in 2005, so it originated from formal methods, but it was kind of one technique which was not very hard to apply.
This was broken, sorry.
Yeah. No, so thanks very much for the introduction. So I start a little bit 1 minute ago because, but I know you know everything about it, and you arrive right at the good slides to have an overview of the talk. So I love symbolic execution because it's both formally grounded, so it's nice formal method, and yeah, it works to some extent, but it really helps formal method being applied in a real context, real industrial context, beyond safety critical context. So it comes from safety researchers which were interested in safety and bug finding, but it has been quickly adopted in security. And this is the view I want to see, to discuss during this talk. Usually people take symbolic execution as it is and try to use it to find bugs in security context. But the question I want to ask in this talk is how can we use symbolic execution in a security context, and especially how is it different than using it in a safety or debugging context? And this talk is a reflection on our experience or a tour on our experience in the BINSEC team on adapting symbolic execution to several binary level security contexts. So it's not very technical, it's more an overview. And okay, I am strongly biased toward code level security and implementation flow rather than logical flow. Actually, that's also a very timely talk because very recently at NDSS, Patrice Godefroy has been awarded Test of Time Award for his paper on automatic white box fuzz testing. So there is fuzzing in the title, but this is really about symbolic execution. So that was a nice move, but okay, it was from 2008, and it make a very, very big impact in the security community. So this is probably the starting point of symbolic execution for security. Just a few things more about me so that you know my bias, which can be in this talk. So first of all, I am very interested in binary level security analysis. So there are a number of scenarios where it can be very, very useful. So for example, most of the time when you want to verify some code, to check some code, you don't have all the source code. Maybe you develop part of it, but there are often some part of it you don't have. You have only the executable, typically for intellectual property reason. It can happen also that you are interested in very precise verification. So if you verify at the source level, let us imagine you have all the source program, the source, and you do the verification at this level, then you can miss some bugs which may be introduced by compiler. So especially for security, the compilers are not really designed to preserve security properties. That's a big line of work in compilers. But so if you take normal standard compiler, there may be some problem there. So if you are able to check the binary which is produced by the toolchain, then you can get more bugs than otherwise. Obviously, in some cases, you don't have the source code at all, like for malware, typically. Can be also interesting, for example, if you want to verify protection, which are introduced by some tools, like obfuscators or CFI tools. So if you since they put the protection usually on the binary code, you need to analyze the program at this level. And sometimes, I will talk a bit about it, you want to go even deeper than binary code, more microarchitectural reasoning. For example, if you want to take into consideration attacks like Spectre or Meltdown. A few words about the BINSEC tool. I won't talk a lot about it after. So what is BINSEC? So it's a prototype tool, and basically we try to bring formal methods to binary level security analysis. So we have different kind of case studies. Sometimes we just try to find bugs and break things. Sometimes we try to prove that things are secure, and we have also some ongoing work on protecting software. So basically, we have a multi-architecture support. So we take some front end to some known architectures. Then we translate that to some intermediate representation, which is small and easy to deal with. On that, we have mainly a symbolic execution engine, which is mostly to find bugs. We'll talk about that today. And we have also some static analysis, which to consider all the path. And then we have different applications, but you will see that. Okay, how is the talk structure? So I will start with a bit of background on formal method and symbolic execution. Then I will present some variant of symbolic execution for security. I'm not sure there are 5 of them, but that was a nice title. And then we go for a conclusion. Okay, just a few words about formal methods for people who have never heard of it. So basically, you can think of formal method as a kind of intersection between software engineering and theoretical computer science. So at some point in the 70s, basically computers become too big and the program become much larger than before, and most computer science projects were just failing because of bugs. So it's called the software crisis, actually, and it's kind of a birth of software engineering, and there have been lots of try to fix that, from better testing, better development process, and so on. And one of them was formal methods. And the idea, the dream, was to prove correctness of a program in a mathematical way, like you can prove a theorem. That looks like a dream. If you want to do that, you have to define the semantic of a program. So you have to define mathematically what are the execution of a program. You have to be very clear on the kind of property you want, and you have to design an algorithm to check that indeed your program satisfies the property. But actually, it looks like a dream, but it works first in regulated safety critical domains. So for example, if you take the latest Airbus plane, there is no unit testing anymore on the most safety critical part. It is all proven by a formal method. You still have testing for integration, but not at unit level. And with time as well, it becomes a success in many more domains. So for example, there have been lots of verification of TLS protocol, cryptographic protocol. Symbolic execution has been heavily used on different Microsoft products and so on. Just a little detour. So we are talking about verifying programs. But this is undecidable. So here, this is Alan Turing, one of computer science key founder. And yeah, actually, we cannot have a program which take another program and terminates and say the program is buggy or not with perfect precision. That's just not possible. But yeah, we know that for a long time, but many people and big founder of formal methods found ways to go around this limitation. So here we have Tony Hoare, Patrick Couzeau, Edmund Clark, and Joseph Sifakis. So this is deductive verification, abstract interpretation, and model checking. And basically, you have several ways to go around this limitation. Especially one thing you can do is to forget perfect precision. And to have analysis which are biased. Either they can prove a program has no bug, but they cannot prove there is one, or they can find real bugs, but they can never say there is none. And this is the kind of technique we'll be interested here. And this is especially important. First, formal method, we are focusing on proof. But in industrial context, it turns out that often people are really interested into bugs, because if your analyzer tells the developer there is no bug, there is not much information because you have to trust the analyzer. But if the analyzer is able to produce a buggy input, then you can just replay it and see if there is a bug or not, and then it gives you information. And especially at the beginning of years 2000, so formal methods was more about proof. And then Patrice Godefroy, who had been standard, let's say, academic people, and then moved to the industry, realized that finding bug was very important, and he came up with symbolic execution. Actually, he rediscovered it. It has been discovered a very long time ago in the 70s, but yeah, now it came back. So what's the idea of symbolic execution? It's actually kind of simple. The idea is to realize that, okay, analysis program is very hard, but now if you take only one execution path of the program, so let's say you go here, then you take this branch, then you take this branch, you see, you just unroll one path. Then it's very easy to compute a formula that we will call a path predicate, which represent the input-output relationship over this execution path. So how the input must behave so that we really follow the path and get the value we want. So this is a formula, and it has nice property because it's quantifier free. There is no quantifier, so usually we can solve them. And if we find a solution of the formula, then this is an input that follow the path. So basically you follow here, you get a formula, you send it to an automated solver. If you get a solution, you get an input which is ensured to follow this path at runtime. And this is even if and only if here. And this is purely automated. So this is very nice for several reasons. This is completely automated. And it can find real bugs because if it hits a bug, you have an input and you can replay it and get the bug. And also if you do it well, this is still formally grounded. So this is technically an under approximation. And you can do what we call bounded verification. So you cannot do full verification because you cannot unroll all the path. But what you can say, if you are able to explore all paths up to length k, then you can, and you find no bug, then you can say there is no bug up to this length. So typically for cryptographic protocol, this is interesting because it will correspond to there is no bugs for a certain size of key. And also it turns out to be very flexible for various reasons because you can combine it with dynamic execution. And this allows to give some easy, to parameterize some kind of trade-off between how generic you are and how robust you can be on complex code. So it is why it has been such a big, big success. So just one example. So let's say we have this path. So we have this instruction where we take new input, then we do some computation, then we take this branch on the true side, this branch on the false side. What does it look like to create the path predicate, the formula? Then you will see it's very, very easy. So this is let's say mostly, it is not exactly written like that, but this is mostly SMT-lib format, which is a standard input format for SMT or SMT automated solver. So we'll first create a temporary variable here, which take the value of variable y at line 0, the initial one, plus 1. So this is w at line 1. Then we'll create here a new variable, which is the value of x at line 2, and it takes the value of w at line 1 plus 3. And then here, if we want to go to true, then x, this current x must be strictly less than 2 times this current z, which actually translates like that. And then here, if we want to take false, it translates like that. So it's very, very easy and automated to create this path predicate. Then we send it to SMT solver, which is nice. There is some common format language, some common format input format. You can use several of them. They are all strength and weakness, so you can even use them in parallel. And if you get one solution, for example here, initial y is 0 and initial z is 3, then you can put them here and you will follow the intended path at runtime. So that's the basic idea of symbolic execution. And obviously, if you iterate that a lot, what you will get is a test suite where each new test input covers a new path. So compared to fuzzing, typically, it will be, in fuzzing, it's easy to get new input, but most of the input are redundant. Here, you are ensured that every new input reach a new path. And you can achieve very strong coverage. Okay, so there have been lots of literature in this in this domain. So there are mostly two key ingredients: how you crawl along the path space, so the path search, and then once you have created the path predicate, how you solve them. And these are the two challenges of symbolic execution. Usually the programs are big, then you have a path explosion. So how can you combat this path explosion? Sometimes even the number of paths is infinite. So you must only put some bound, but sometimes you can do better. And also for some kind of programs, it can happen that constraint solving is too expensive. So how can you deal with that? And along the years, there have been many optimizations. So for constraint solving, you have lots of dedicated pre-processing. You can have some caching and solution reuse and so on. For search heuristic, you have different heuristics, some path pruning, some merging, and so on. So you can prune path according to the past. So if you have already seen some similar path, then you filter it, or according to the future. So if the path cannot reach the kind of statement you want, then you remove it, and so on. Okay, and in the end, yeah, that's very successful. So just for the record, so what was this paper about by Patrice Godefroy and co-authors? So this is not exactly this paper. This one must be a communication of the ACM, or a later one, but that's the same idea. So actually it was at Microsoft, so the team of Patrice Godefroy, they developed the tool Sage, which is a big success. So this is symbolic execution. And basically, from what I understand, in Microsoft, when some project is security critical, once it is done, it must go to some server which are running Sage. So it comes after static analysis, it comes after fuzzing, and then they run Sage on it for hours or day and so on, and try to find bugs. And with that, they have found many bugs. I think the first one they use it when on Windows 10, also the Office of that time. So they use it on very big program, and they found lots and lots of bugs before they got shipped in production. And in the paper, especially the authors make the point that this is by far the largest use at the time of formal methods in an industrial context. So that was a very huge success. Okay, so that was the beginning of symbolic execution. So how can we use it for security? Which kind of problem may happen in some scenario, and how we can try to deal with it. So this is the core of the talk. So we'll try to see, depending on the timing, different usage. So first the standard usage, and then some variation, like robust, which correspond mostly to some work of our team. This is kind of a panorama. So we'll go into that. So first, just to make things clear, so if you have simply symbolic execution, so you are able to crawl path in some way, to explore path, one path at a time, okay? Then you get intensive path exploration, which is very good because the more path you are covering, the more chance you have to get some bugs. So obviously there is a challenge with path explosion, but actually you can do even better because when you create your constraint along the path, every time you have a kind of dangerous instruction, for example, pointer dereference or memory access, you can add extra security condition and check if this condition can be violated along this path. So for example, if you have some memory access, you can add some extra check where you try to follow the path and access to memory address 0 or access to out-of-bound memory. If the solver says it's satisfiable, then you get input where when you run them, you follow the path and, for example, you dereference the null pointer. So you get a real bug. Or you just go do some memory buffer overflow. So if you do that, then yeah, it's typically what Sage does. Then you are able to find typical critical bug. So there are also many other tools, like one of the most popular is CLI by Christian Kadar and team at Imperial College. There have been also pioneering work by Kushik Sen, Vijay Ganesh, and more people. You can also go a bit further if you want. I will not dwell into that, but it's interesting to know it. So this is pioneering. This has been pioneered by Sean Elan and then worked by David Bromley and team. You can also directly create some kind of simple exploit, because if now you follow the path and ask a constraint to do some buffer overflow, and add a constraint such that you rewrite the stack pointer and write some kind of payload into the stack, then if the solver gives you an input, it is an input which trigger a bug, rewrite, put your payload into the stack, and actually rewrite the return address, the program pointer, so that the next instruction will go to this payload, and you directly create some simple exploit. Okay, this exploit won't work when you have protection, but that's a way you can also use this technique. So this is very powerful and appealing. So it leads to automatic exploit generation. So just starting to view a new thing. So what about, for example, very hard to find bugs? Because symbolic execution is actually very good for kind of buffer overflow, where the error is very local. But if you think of, for example, use after free bugs, these are the kind of bug where you allocate some memory. Then at some point you have some pointer on the memory. Then you deallocate the memory, but there is still some pointer on it, which is called a dangling pointer. And later on, you access the pointer. And if you are if the defender is kind of unlucky, the memory is still pointing to some secret, for example, and you can get some leak. This is very hard to do with symbolic execution, because now you want to do more than just finding a location in the code. You want to find sequence, and then this is very, very hard. So what you can do, for example, and that was common work with Jocelyn Fest and Robin David. So Jocelyn was PhD student at Université Grenoble, and Robin was one of my students, where you can try to use cheap static execution analysis to guide your symbolic execution. So in our case, we had a very simple static analyzer called Gabe, simple but very useful actually. And Gabe was able to give you this kind of information, this kind of hull, which basically, if I start here and my execution stay within this part of the program, and I reach this tree, and then I will reach this use by staying inside this part of the program, then maybe I have a use after free bug. So when you have this kind of hull, this kind of subspace, then you can launch symbolic execution with some frontier. You limit the search. And so if your static analyzer is able to give you some kind of tight hull, then it will help a lot symbolic execution, and you can find more easily a complex bug. So that's also one thing which is nice with symbolic execution. You can combine it with other standard techniques. Okay, so that was the standard usage actually. So let us see some more tricky, some problems that can happen with symbolic execution and how to try to get around them. So one problem. It turns out that when you come from safety, in some way, all the bugs are the same. Anyway, if you work in aeronautics, you don't want any bug. So any bug is fixed. So all the bugs have equal importance. If you're in security, or let's say in other place than safety critical industry, it's not true anymore. If you look at any big open source project, they have lots of open bugs. So typically there are many bugs which are not closed, not fixed. Why? Because developers just cannot fix everything. And also sometimes they are afraid that by fixing something, they make another mistake, which is very dangerous. So in some way, there is the idea that some bugs are more valuable than the others, and you try to care and fix the important bugs, and you don't really care of the others. But symbolic execution is not about that. So typically, you can have problem. So this is joint work with Guillaume Girol and Benjamin Farinier. So Benjamin is in postdoc now. He was one of my students, and Guillaume is still one of my PhD students. So let us see a very simple problem which exemplifies that. In practice, it turned out that symbolic execution can produce, let's say, practical false positive. I say practical because normally symbolic execution doesn't produce false positive. When you get an input and you say it can reach some place in the code, it's supposed to be right. But it's right from the reachability point of view. And maybe normal reachability may not be very good here. So let's take this little program here. We have two different sorts of input. Here we have real input, but we can just enter. And here we have another kind of input, but which is more of environment. It's kind of random. You do not control it. You read something, but you don't know what. Then, okay, we want to arrive here, so we have to solve this condition. If you use symbolic execution, it will just tell you, okay, you have to solve this. So here is one solution. Okay, but is it good? Maybe not, because what you can enter are the value of A and B, and you don't control X. So if symbolic execution tell you you should do that, the problem, the only thing you can input are the value of A and B. And if X change a little bit, actually is not 0, then you will not enter. One thing, so for example, this input is not a solution anymore. So from the formalization point of view, it's not a false positive, but from the practitioner point of view, this is a false positive and this is a problem. And actually, it can happen in several important scenarios in security. So for example, if you do some symbolic execution on binary code, and at some point you have some canary, and the canary value is random, then the symbolic execution will simply tell you, okay, that's very easy to go through this path and bypass the canary. You just have to have as argument the value of the canary, and that's it. Yeah, okay, but in practice, you don't know the value of the canary. That's the point. So in practice, here you have a problem. So, and you have many more ways of having this kind of false positive problem in some way. So symbolic execution can guess all the randomization-based protection. You have also bugs involving an initialized memory, where the symbolic execution will just take advantage of an initialized part to say, okay, maybe the secret is in this uninitialized part, so now I know it. It can take advantage of undefined behavior and so on. So this can be a problem on some tricky program. So our proposal is to, basically in our paper, we propose a new formalization that we call robust symbolic execution. So we have now two sets of input, the one we can control and the one we cannot. And while in reachability, you basically want to find an input such that it reaches a location or a predicate. Now we want to find a control input such that whatever the control input, we will reach the location. So if we have that, think now of the attacker point of view. If you find such a bug, it's not that good for the attacker because, okay, he can control A, but he never knows the value of X, so he doesn't know if its attack will work or not. Now, if you can find this is very, very good for the attacker because he knows that he is able to have some input such that whatever the environment does, it will lead to the attack. So obviously, robust, if you are able to provide some robust input, it's much more dangerous than non-robust one. So basically in the paper, we just rephrase all the symbolic execution framework to see what must be changed or not, and how complicated it is to add this extra quantifier. Yeah, regarding the time. So typically here is one example on some benchmark we have. So I won't go into all the detail, but let's say this is standard symbolic execution, and this is our best robust symbolic execution version. So here we find correct bugs in 30 examples out of 46, but there are 16 cases where symbolic execution says there is a bug, while actually this is a false positive. This is the problem. And by using our robust symbolic execution engine, actually we can find correct bugs in 44. So all the examples are buggy, But what we want is not only to save their buggies, to find input which indeed show their buggy. So with our robust symbolic execution engine, we are able to find the right buggy input for 45 of them, no false positive. And since it's more costly, we have some timeout in 2 cases. But we avoid here the false positive, and that's very important in practice. So we have also some different study on existing CV to try to see if we are indeed able to prove them robustly reachable. So we managed to do it in some case. So this is still, I mean, early work. Clearly, it's not as mature as standard symbolic execution, but we think this robust symbolic execution and this robust reachability problem is something which is interesting and which brings some value in security context. We have also some work, but it's just so obviously one easy idea is to use some solver with quantifiers, but it's hard. We have also a way, some years ago, we have proposed some way to basically reduce the generating a model for quantified formula to the quantifier-free case. So there is an approximation. So if we find a solution, then this is a real solution of the quantified case. But if we say there is no solution, maybe there was. But yeah, it's also interesting because it allows to reuse the whole SMT machinery. So that was one problem. What happened when you want to get some kind of replicable bugs and not just simple bugs? Another case that can happen in security is that typically symbolic execution is very good for bugs like memory buffer overflow or null pointer dereference. But in security, we are interested in more kind of bugs. So typically, one important class is information leakage. And this kind of problem is not typical properties. So usually what we look at in standard symbolic execution is called safety properties. And here we must look at hyper safety properties. What it means is that we are considering pairs of execution. And if there are observable difference, then there is a problem. So let us imagine cryptographic primitive, and the attackers want to guess the secret. And what he will do, he has public input and secret input. So he wants to guess the secret, but he can provide only the public input. But what he knows is that there are different values of secret, and some of them take different time to execute. So if he provides the right public input, then he observes time, and depending on if it observes this time, he deduces that the secret is this one. If he observes this time, he deduces that the secret is this one. So we really want to reason about all the possible pairs of execution. So this is something which is not covered by standard symbolic execution. So this is work with Leslie and Daniel, who is now at KU Leuven, and Tamara Resk as well. So basically, what were several. So from a security perspective, this is very important because it encompasses timing attack and cache attacks on crypto primitive, and with mostly the same framework, we can also deal with secret erasure. Okay. From the symbolic execution point of view, this is kind of complicated and tricky because we have basically two problems. The first one is that potentially we must follow all the pairs of execution. So there is a quadratic explosion of the number of paths. And also the kind of constraints we have are much more complicated because in some way each constraint encompasses two paths at the same time. We want to say, okay, we have this path, and the public input are the same and the secret input are different, and I want to be the observation to be different. And solvers do not really like that. Also, we have to check it very often because typically in the case of timing attacks, you have to check it at every branch instruction and every memory access instruction. So you have a huge amount of extra queries for security. So just regarding the path explosion, so since we are considering, we are reducing the problem to checking what we call constant time programming, meaning that we want to check that memory access and branch do not depend on secret. So it means that we are limiting ourselves to execution which follow the same path. So we don't have this kind of explosion. Still, we have the other problem that the constraints are more complicated and that we have to check extra security constraint at mostly every instruction. So we must be very, very, very efficient in that. So what we have done with Leslie is basically we take a tool which is called Relational Symbolic Execution, which looks like what I show you, except that instead of a path predicate, you have a kind of relational path predicate, which represent two execution. But the idea is to make it affordable. We have kind of a sharing mechanism suitable to binary level memory, which was not the case of other attempt in prior state. And we have also some heavy constraint preprocessing. And with all of that, we managed to actually discard many insecurity query in advance and to get much, much better performance. So typically compared to standard implementation, on some example, we have 2 orders, we are 2 orders of magnitude faster. And it allowed us to perform very large scale case study where we took lots of crypto code samples, compiled with different options on different architectures, and we try to find bugs on them. So we proved most of them correct actually, but interestingly, we find 3 new bugs on code that were previously formally verified, either on source code or on LLVM code. So showing that actually this is very important to perform such analysis on binary code. We had also some hints on the kind of option of GCC and Clang, which actually can help secure this kind of, enforce this kind of property or add problems. And one also interesting aspect is that this kind of study had already been done by David Chisnall, but manually. And so with our framework, we are able to completely automate it. We are also finding some potential issue in some protection scheme. Okay, so this is another problem. Sometimes you want to go beyond the standard bugs that people are looking in safety. And so we want to have more complicated things. Now, third problem. What if the attacker can observe more behavior than what you expected? Okay, so we are already at binary level, so it's kind of low. But if you think of all these specters and meltdown attack, actually these attacks happen because of what we call speculative behavior in processor, which has kind of optimization where the processor will do some computation in advance, just in case. So then if the result of so typically at some branch, the processor will just guess which branch will be taken. Then he starts doing the computation in advance. If the execution really takes the good branch, then all this forward computation is a gain because now we keep it and we just continue. If in the end the execution chooses the other branch, then the speculative execution is revert. But what happened some years ago is that some researchers discovered that actually not everything is reverted. You can have some kind of side channel microarchitectural. You still have effect at the microarchitectural state, and you can use that to have side channel attack. Okay, what happened from the formal perspective? The thing is, it's like now you have much more behavior. You have a normal path of your program, but you have also all the speculative path, which depend on the kind of speculation you want to check. So for example, if you are just looking at speculation on branch, then now you must consider that when you encounter a path, a branch, and you are still allowed to do some speculation, then you can take whatever side you want. And then later you will have to check if it was the good one. But for some amount of time, you are allowed to take some branch which is not very compatible with your current state. And you have the same, for example, from some return instruction for memory access and so on. So you have now much, much more possible path. And there is a big explosion. So we have a very simple test, not a lot of instruction. So for example, for some example, in the sequential semantic, normal semantic, you have 14 paths. And when you put the speculation and memory, you end up with 37 million paths. So there is a very huge explosion. So you cannot just consider all these extra paths in a naive way. So what we have done on that is basically to have a smart encoding on speculation. And you can see them as kind of dedicated merge plus targeted simplification to avoid this, this forking, this extra forking as much as possible, and try to have mostly no explosion due to speculation. We still have the explosion due to the program, the sequential semantic, but mostly not due to speculation. So what happened with that? So we did lots of experiment on that. So there was a few previous work. So very few techniques. So this one is speculation on the branch, and this one is speculation on memory. So typically, if we take at binary level, so when it's red, it doesn't scale a lot. Orange, it's kind of okay on small example, and green, it's okay for typical cryptographic primitive. We don't pretend it scales to the Linux kernel. It's still cryptographic primitive. So basically for speculation and branch, our techniques show to be much better than previous work and scale rather well and we also are able to find timing and caching attacks. And for memory speculation, our techniques is probably not yet ready for big crypto primitive, but there was very, very few prior attempts for that. And they had a clear scaling issue. So we provide the first reasonable tool for this kind of things. And we have also done lots of case study, and especially, for example, as fun fact, we have found that, for example, some protection for this variant of specters were actually vulnerable to other variant of Spectre. So this is the interest of having this kind of completely automated framework. Very quickly. Now, last problem. Okay, symbolic execution is about one solution, is about getting one solution per path. But sometimes we would like to have a lot of them. And if you want to do that with symbolic, so for example, think of a case where you want to combine a fuzzer with symbolic execution. So one way to do it, like in Driller, is when there is some path which touch some branch that the fuzzer has lots of difficulties to cover, then it sends it to the symbolic execution tool, which try to find one solution. But fuzzing is about having lots of solutions. So if you want to do that with symbolic execution, what you can do is when you get your predicate, you ask the solver for one solution, then you ask it for another one, then you ask it for another one, but it's very expensive. So it's, in some way, you add smartness to your initial fuzzer, but it comes with a very big price, and so it's not clear that you will win in the end. So what we are looking at with Yael Vincent is to see how we could redesign in some way symbolic execution to be more oriented toward a solution enumeration and in the end having better combination with fuzzing. So we came up, so this is mostly work in progress. So we came up with the idea of lightweight symbolic execution, where the idea now is that we don't compute an arbitrary path predicate, but we restrict ourselves to some family of path predicate which are for which it is very, very easy to enumerate solution. So now, in some way, computing the path predicate was very easy before, now it's more complicated. But on the other end, now we can enumerate as many solutions as we want. Each new solution just come in constant time. It's very, very easy. And so it integrates better with fuzzing. So again, this is the kind of problem that you will not really face if you are just from the safety side. I think I have still the time for this one. Okay, a little bonus. Why is it in bonus? First, because I had already my 5, and actually it's more about reverse than about vulnerability. But just so symbolic execution is really about reachability. You want to find input that reach some place and some bug in your code. But sometimes, and it's nice for that. But sometimes you really need full proof. You really want to check that something is not feasible. So, for example, if you do some reverse and you try to understand some complicated code, sometimes it's very important to know that one branch is just, you just cannot take it. There is no execution that can go through it. So what we can do with that? So by definition, symbolic execution is not adapted, because if you want to prove that something is not possible, you have to you have to do it along all the path, and with symbolic execution, you can only explore a part of them. But what you can do is to use your symbolic execution in a local manner and in a backward bounded manner. So you start from the property you want to prove, you go a few steps backward, like case step, this is a parameter. Now you get a formula. You get a formula which represents all intermediate states that can reach your predicate in K computation step. You solve it. Now if you get a solution, you are not sure it's a real solution, because you don't know if this intermediate step here are already reachable or not. But if there is no solution, then you have proved that your predicate is not feasible. Because basically what you prove is that you cannot be closer to case step than the property you want. So you can never reach. So with that, you can prove things. Another good thing is that it's completely local. So it doesn't depend on the number, on the size of a program. So it's much more scalable. But obviously then you have this predicate K. So if you put a very large K, you will encounter scalability issue. But with a reasonable K, you can already do interesting stuff. So just for the record, we have used it on some kind of APT grade malware, which was very, there was lots of protection, so lots of predicates were non-feasible by design. And so we use the techniques to prove that 40% of the code was not reachable. And so the code was around between 400,000 and 500,000 instruction. And at the time, we did it fully automatically in less than 3 hours. And now we do it in 12 minutes. Okay, time to go to the conclusion. One first point is that, okay, so this is, first we see that actually symbolic execution is kind of flexible. So going to security, you have new kind of problems, which are interesting problems. But yeah, so you can adapt symbolic execution for them, but you must also take care and really tune the technology, because if you only rely on SMT solver in a naive way, okay, they are very, very powerful. That's great. But the kind of problem you encounter are also very complicated problems. And so finely tuning the algorithm, trying to put as much knowledge from the domain and from the issue you are trying to solve inside dedicated search heuristic, dedicated pre-processing, constraint solving, and so on, really make a huge difference. I won't go more on that. So as a conclusion, so I still love symbolic execution because it's formal and it works, at least in some context. What is interesting, if you try to take it from its initial safety-oriented purpose and try to use it in security, so sure, it will work for some application, like trying to find buffer overflow. You already get something, which is nice. But quickly, you will end up also in problems that were maybe not expected, like maybe you don't want to check the same security properties. You can have this problem of some bugs are more important than the other. You can have this problem of what is the attacker able to observe and these kind of things. Good news, symbolic execution is flexible enough to accommodate that. And also good news, that's really new exciting theoretical question. So from my point of view, this is very interesting direction, because on the one side, you get new interesting problem from the theoretical work. On the other side, from the system security side, if you manage to solve this problem, then you bring some value to the security community. Also, you have some work on understanding the problem, but it also comes with complicated algorithmic issue and so on. So it's very interesting. And So I guess this is a very, very fruitful and interesting direction, and there are still many exciting challenges ahead. So most of the results I have shown you are implemented in the BINSEC platform. The code is open source. Anyway, for what is not available in the public version, we do have artifact on the website for replicability. If something doesn't work as you expected, do not hesitate to send us email. So now we have, especially we have Frédéric Recoules, which works full-time on the BINSEC prototype. Now he's doing an amazing job. So we had a Christmas release, and now we have a spring release. Soon we'll have RISC-V 64 bits, and we have also some optimization which are coming. So we have many things which are happening. So do not hesitate to check the website often. And we're also always looking for PhD and postdoc and collaboration. That's it for myself. Thank you for your attention, and I will be happy to take questions.
Thank you, Sebastien, very much. It was really very nice walk through different shades of symbolic execution. And if anybody has any question, they can actually either write on the question answer panel or because I don't see any question written. But while we are waiting for somebody to ask some question, maybe I was just wondering, because in one of the slides in the beginning, you were talking about I think you mentioned somewhere about the taint variable, something like that. One of the early slides. Taint, something to do with taint.
Taint? Oh, okay. So let us see.
There was.
You tell me when you see it.
Yeah, I will. Okay, go back.
Not really sure you talk about taint, but
there was variable, like you were talking about that this is how we will do some. So this was your first slide, initial slide, and after that, I think.
Do you remember the problem actually?
It's where, okay, go back. It is somewhere you were talking about some of the like variables, like maybe here, yeah, and go back. It's a path, I think something related to maybe explosion.
Yeah, no, okay, intent. Okay, I see where it is. Okay.
Yeah.
Yeah. Sorry, that's kind of maybe.
Yes, taint variable constants.
Okay. So that's okay. That's very technical. I don't know if I should have put this slide. So you are coming. So that's the way we are. You know, we have this robust reachability problem. We don't want to find just input, but we want input which are replicable actually. So now we have to solve something which are some quantifiers. So first, when we did this work, so in 2018, solvers were very bad for finding models with formula with quantifiers. They were good at proving that a formula with quantifiers was unsat, but were not good at finding models. So actually, 3 years later, they have done lots of progress. So there is also one solution, which is you just take a solver which is able to deal with model generation for quantifiers. But let us imagine that your grids, the solver you prefer, is only quantifier free. So we have a reduction for that from the quantified case to the quantifier free case. So what we do is it's kind of a TAN, but it's more like an inspiration. It's not really a program TAN. So let us imagine we have this formula. So we have a problem with this formula. So what we do is that basically we will build a quantifier free formula. And for each of the variable, we will add a new variable, which is the same name with a circle, a black circle, okay, which represent, so I haven't said it for a long time, so I don't remember how it reads, but basically it represents, if a variable can depend or not on this quantified input. Okay, so initially, typically, x with a dot will be at true, I think. No, it is at false. Okay, so it represents if it is independent from the quantified variable. So obviously this one will be at false because it depends. And this one, which are initial, will be at true. Then you compute the same morally for each of the term. And we compute what we call an independence condition. And basically this encoding will say that, okay, in the end, if we want to find input which are independent from X, then either A is independent from X and X is independent from X, but the solver will find that it's not possible. Or X is independent from X and X is equal to 0, because if we manage to put this one to nullify, then it absorbs the tent, but it's not possible because X is not independent. Or A is independent from X and it can be 0. And we also need that B is independent from X. But this one is okay because it's true, actually. And then the solver will simplify it. So it will see that this one is not possible, this one is not possible. So in the end, what he will say is that, okay, you need to find, to put A equal to 0. And then the complete formula we will solve is this one without the solver plus this independent condition. So it will be this one and A equals 0. Because you know we can do it like just a pure tent, but like okay, if it's completely independent, there is no problem. But we can also impose some. At some point, we see that we have some expression which depend, but actually we can choose one of the operand so that it nullifies the tent in some way. And then it's the solver which will find exactly what must be done. So then here, it will find a solution. It put whatever solution goes for B, but it will force A to be 0. And so if A is 0, then X has no more impact. And we get what we want. Okay. You see the idea?
Yes. Yeah, actually, we have been working on.
But it's really, you know, it's kind of thin propagation, but which is really built in inside the formula, so that it's the solver who chooses the thing, how the things should go.
Yeah, exactly. Because we have been looking at the similar thing, but from the, you know, really the taint propagation point of view, as we see now, like really the input which is tainted and it is flowing, and we were actually trying to see if there is a way of, you know, somehow reduce the constant bloat, because you sometimes do a lot of constant collections, but the idea is to, you know, somehow prune these constants as much as we can.
Here, since the point is compared to standard tent propagation, you know, usually you have this kind of rule in tent propagation that if A is equal to 0, then A dot X is not tainted. But you need to be sure to have A is equal to 0. Here, with our encoding, the solver will choose A is equal to 0 if he needs it. You have also the same thing with aliasing. Let's say that in your memory, you have two values, one which is tainted and one which is not. Then with our rule, the solver will detect it and will try to put some index which try to read the untainted value, actually. But then you have, then the details are in the paper. And obviously, there is a part of the transformation which is generic, which works for everything, and which is basically, if all the operands are untainted, if I want a term to be untainted, that I must try to have all the terms untainted. And then you have also some more theory-dependent encoding, which is typically, okay, for operator times, one thing I can also do is to try to enforce that A is 0 or X is 0 and so on. And so then it depends on exactly what you put in your inference rule. But that's the idea.
All right. Yeah, that makes sense. Okay, so we are actually quite ahead of time and I don't see any questions. So maybe it's time to thank you, Sebastien, for your very interesting talk and your time. And he has a question. Yes, Alex is asking a question.
Okay, so for the first question, you are pointing one of the big problem of symbolic execution, but I would say one of the big problem in any program analysis is scalability. And indeed, one big issue in symbolic execution, it's not easy to, people do not really understand how we could use some kind of summary of libraries actually, because since we want to be very precise, like for example, in a static analysis, if you don't really know about a library, you can just say, okay, it's stop. I don't really know what it does, but it changes only this value, for example. Maybe it's not very good, but at least it is sound. We don't really have that for symbolic execution. So that's a big problem. So one thing is to provide stuff for a library, but it's a huge work. You know, there have been some work, but for example, by Patrice Godefroy, where he kind of pre-build some kind of exploration tree for some libraries. Yeah, I guess it helps in some context. There are also some work by for string library by Christian Cadar in CLI, where they encode string library in a specific way that Z3 is very good on it. And so when they see this kind of library, then they have an encoding which is very, very good. Yeah, but honestly, this is a very one big challenge for symbolic execution. So I guess at the moment there is no very, very good solution. Regarding your second question, the problem with AI, one problem I would say for vulnerability detection in general, is that what do you, if you're, one very important thing is not only to say this code as a bug, but it's to be able to give the input which lead to the bug, or at least something very precise about the bug, so that expert can look at it and decide if it's a bug or not and fix it. So I've been reviewing some machine learning based paper about vulnerability detection, but often they just say, okay, this is buggy, but what do you do with that? Because I mean, if you push the argument to the limit, you have a very simple way. As long as it is a C program and it's 1,000 line of code, you can just answer this is buggy and you are probably right. So one thing which is very, very maybe lacking, at least in some of the work I have seen in this domain, is to be able to not only say it's buggy, but to be kind of precise about where it is buggy and why. So that's the first point. Another point is that machine learning based by techniques, by definition, I guess they are more they are more tailored to finding one-day vulnerabilities. So kind of vulnerability that have already been seen in similar program, or even in the same program, same line of programs, while symbolic execution can in principle find 0 day. But then again, you could also say that it's a bit stupid in the case of symbolic execution, but it's because it's like we restart everything for every new program and every run, while we could take advantage of knowledge of known bugs or known kind of similar program. So from that point of view, I don't think it will replace, but probably there are lots of things to, you know, they are kind of complementary. So I hope it answers to your question. So for Bilal Sharif, so so I didn't work myself on concurrency. I know there has been some variation of symbolic execution for concurrency. The way it works, usually you have two things. So first, if you have a concurrent program, but you are not able to, you have nothing smart, you can still use the concretization. So look dynamically which thread interleaving as you are used, and you follow this one. So if you are lucky, you will find the bug. So first, okay, that's luck. There are also some variation of symbolic execution where people fork not only on path, but also on interleaving. But you have to model the front interleaving mechanism and so on. You can do that. So I guess they can probably on some example find this kind of bugs, but then you have the usual problem. You have the explosion of thread interleaving multiplied by the explosion of symbolic execution. So some people doing that have also reuse some result from model checking, from old model checking, which was very about taming the explosion due to interleaving. So you have techniques like partial orders to try to remove some redundant thread interleaving and this kind of thing. But yeah, that's clearly another level of difficulty. So it's, but there is some literature on it, even if I am not very good on it. Okay, so regarding the further, so that was only on the last part of, very last part of my talk, the work in progress. Actually, this part I was quick, but we can see it in two ways. So either we use only symbolic execution, there is no further, but the symbolic execution itself now is able to enumerate solution. Probably less quick than a further will do, but much quicker than normal symbolic execution. And then there is still more reasoning than in a further. But you can also combine both. And in that case, it's kind of a driller combination. So at some point, the further just have big difficulties with some branch. It doesn't manage to do it. So he gives the corresponding task to the symbolic execution tool. But instead of returning a single input, then the symbolic execution, if it uses lightweight symbolic execution and works, then it will enumerate lots of solutions and return them to the fuzzer, which now will have lots of choice regarding this branch it wasn't really able to fire before.
All right, so I think we have reached to the end of this seminar, and as I said, I was saying that this is indeed a very interesting seminar, especially from the the 5 shades of symbolic execution. Means, okay, in what way people have been using it, what you can do, what are the possibilities. So it has all these kind of directions, which is definitely very interesting, especially for young researchers who are trying to think about some new directions. So Sebastien, thank you very much for your time. We don't have normal stage to clap, but assume that it is clapping for you. And and everybody, thank you very much for your time and attending the seminar. So you see, Blair is saying clap, clap.
Thanks, Sanjay, for the invitation, and I was very happy to see you are becoming a successful senior researchers. It's always nice to see people you have seen in postdoc or PhD student, and you see them growing. That's a very interesting part of the job. Okay, thanks all people who attended the talk, and anyway, Sanjay, we try to have a meeting, another meeting soon. Bye.
Yes. Okay, fine. Bye. Thanks a lot, everybody. Thanks a lot.